Oops, hold on one second. Okay. Welcome, everybody. I think let's give that a second. Does that look all right? Yeah, that looks good. Okay, welcome, everybody. So we have 3 classes remaining, including today. And the reality is the last class, we won't really have much to go over because we will have essentially covered the material that needs to be covered, right? Because we're going to cover conics on Tuesday, and then I'll cover sequences and series. But and remember, you're not tested on sequences and series. We're going over it, and then you have to do the homework. So I guess we will still have more stuff to do on that last day. But then you have to make sure you're getting, absolutely get your tests taken care of. There's just no time for you to go into the next week. It's too late. I have to be submitting grades. So make sure that you have your tests taken care of, all set up and ready to go. Make sure that you get the test taken, and then and that you're getting all the homework done and stuff like that. If you end up having like a real reason why you end up missing the test next week, like you have COVID or something and you're not supposed to go to the testing center, let me know. But unfortunately, what that means is you're going to end up with an incomplete in the class, which is a bit pain, right? You don't want to do that. So, and I'll have to have like some kind of medical documentation for that. I can't just sort of take people's word for it. So, there's a question here. Will the final be curved? I have no idea. Until I see scores, who knows? Right. There's no way for me to know ahead of time. What if everyone gets 100% on it? Then, I don't really know. So there's not much I can do until the scores come in. So I don't know how that'll work out. Okay. So make sure you get your test in. Make sure you get your homework completed. I know I said I was going to add some more stuff to Canvas, but I can tell everyone's very busy at this point. You're just trying to get the homework done. So I don't really want to pile on too much. Just make sure you're spending the time getting those homework assignments done. Every point you get in the homework is raising your grade a little bit, right? And it's a guaranteed raise in your grade. Whereas with the exam, you never quite know how you're going to do on the exam until you're taking the exam, and then you've taken it, and sometimes it doesn't go. Even if you prepared well, sometimes an exam doesn't go how you wanted it to go. But working on those homework assignments is guaranteed. Each point you get on the homework is lifting your grade up a little tiny bit. So make sure you get it up there. Make sure you get the stuff done that you need to. Also, like I say, when it comes to grades that are borderline, like right on the edge of a D or C or a B or C or something like that, if they're right on the edge, if you don't have a very good homework score, then there's not much of a case that you should be given that bump up to the next grade because you didn't really put in the effort to complete most of the homework. So you really want to finish this class with your homework scores up in the 90% somewhere. 90-something kind of shows that at least you made a legitimate effort to, especially if it's like 93, 94%. That shows you legitimately really tried to do all of the homework and really try to master all of that material. You know what I mean? So like if someone's done the minimal amount of homework and then they're like, oh, well, can you bump my grade up? That's doesn't really work because you should have just done the work and then you'd have the grade that you wanted. So that's kind of the key, right? I'm not trying to, pile on here. I'm just trying to make sure everyone understands the key to that grade you want is by putting in that work, getting the homework done. You do the homework, you'll get those problems right on the test, or you're more likely to, and will go well for you. Also, I posted the practice exam. It's at the very bottom of your Canvas page. Very, very bottom, very last thing. You'll notice this last group, Chapter 7, Sequences and Series, is not on the practice final. That's because we're literally going to be I'm going to be going over that material on Thursday. so I can't really have tested you on it for some of you taking the test Tuesday or Wednesday. And even if you're taking the test Friday, that's not very much time to learn that material to the point where you can do this on exams. I think that's a little bit unreasonable in the summer. So you have to learn the material. There's homework on the material, but you're not going to be tested on that very last chapter, okay? We'll get Chapter 6 taken care of early next week on Tuesday, and then we'll go from there. So is everyone comfortable with how we're going to finish out the next week? I know it seems like there's a lot left, but a week from now we'll be done with the course. So, or at least we'll be done with our class meetings. You'll still have some time to work on the homework. Everyone's good? Everyone's comfortable? Okay, great. And hang in there. You're almost done, right? You're almost done. If you've made it to this part and you're in good standing, like you're almost there. I know it's tiring, but you sacrificed a good chunk of your summer to be successful in this class. Don't give up now, right? You can get there. Okay, with that said, let's look at some stuff. So we are continuing our discussion with systems of equations today. Let me make this a little bigger. Not too big. Maybe that's too big. So we've got things we want to talk about today are matrices and solutions to linear systems. We talked a bit about inconsistent and dependent systems last time, although I go a little bit deeper in here. I've got a discussion on dependent systems, and then there's another video on that. And then we've got determinants in Cramer's rule we'll discuss today. So we've got our meeting, and then you can see here some support videos if you want to see a little bit more. Here's some videos you can watch. Determinants are confusing. I actually think we teach them a little bit too early in mathematics. You don't really need determinants until you're kind of on the other end of the calculus series. And most people don't need to go all the way through the calculus series. So in my opinion, it's a complicated topic we bring up a little earlier than we need to, but it's in the course outline, so I have to teach it. And then we've got nonlinear systems of equations, which you can probably guess pretty much, like you kind of already know the tools that you need in order to solve nonlinear systems of equations. There's a little bit of differences. You have to be a little bit more careful, but basically you're going to be using elimination in much the same way that you did for systems of linear equations, except now things are nonlinear. You get parabolas and circles and different things like that, right? So those are the things we're going to look at today. So let's look at things. So let's jump into matrix solutions and systems. So we've got the homework here. So that is what in the homework they're calling 5.3, solving systems of equations using matrices. And you could imagine, like we've talked about, or I've talked about, how we can have systems of equations that get bigger and bigger and bigger, right? So when we're learning how to do systems of equations by hand, we start with 2 equations in 2 variables, right? And then you saw there's some homework where you do 3 equations in 3 variables, right? And it's really just an extension of what we've already looked at. So I didn't really cover that much in class. It's just a harder version of what we already did. But for those of you who have already worked on that, you can see solving a system of 3 equations and 3 variables is significantly harder than solving 2 equations and 2 variables. And solving systems of equations in 4 equations and 4 variables is significantly harder than 3 equations and 3 variables. And this is how things tend to work with systems of equations. Is the difficulty as the size goes up for these systems is not linear. They don't get a little bit harder each time. It goes up exponentially. So the amount of work it takes to solve a 4x4, that's a 4 equation, 4 variable system of equations, is way, way harder than a 2 equations, 2 variable system of equations. Each time you make it bigger, the level of difficulty goes up significantly, not a little bit, like a lot. And so what that means is, while it's relatively straightforward, I know some of you are still working on it, but hopefully many of you are to the point where you're like, oh yeah, two 2 equations and 2 variables. That's no big deal. I can solve that pretty reliably, pretty comfortable solving that. What happens in real life is our systems of equations that we tend to solve are generally much larger, right? We have simplified versions of the problems that you're working on for homework, but in reality, most of your systems of equations are large, even for like you can use systems of equations to work on networks, right? So even if you're just looking at a portion of the network, those can all of a sudden become a dozen variables, right? Or more, 20 variables all of a sudden. And with the advent of big data, is a term some of you may have heard, because our phones are constantly collecting data on us, right? We like to think, most of us like to think that, oh, well, my phone's just collecting data when I press something on the phone, which is not true at all. Right now, all of our phones are collecting data on us, even though we shouldn't really be on our phones right now. Even if your phone is off to the side and it doesn't look like it's doing anything, data is being collected about you. That's what big data is all about. There are massive, massive amounts of data on all of us that are being collected at all times, assuming you're it's some way on the grid and have a phone and stuff. That data is being collected, and places are crunching that data to figure out the next ad to show you when you look at your app, or what's the next post they should show you to get you a little bit angry so you stay on Facebook a little bit longer, or this is all data that's being crunched about all of us at all times, because that's how they make money. They get us to stay on YouTube a little bit longer, to watch a couple more ads. They get us to stay on Facebook. Who uses Facebook anymore? But anything that has that kind of a system where it's TikTok or whatever, it's all about getting you to stay on there a little bit longer, and data is being crunched about you all the time. These are systems of equations that are being crunched that can have thousands of equations, thousands of variables in them. So as you can imagine, if you applied the same techniques that we use, like we looked at the addition method or the elimination method last time, that would get kind of confusing when you're trying to do that with systems of equations that have thousands of equations and thousands of variables. That would get very confusing. So generally what we do is we hand that stuff over to computers. Well, the way that computers handle systems of equations is generally in what we call a matrix. And the plural of matrix is matrices. And it's just a mathematical object that allows us to deal with systems of equations in a much, much more efficient way. I can kind of show you here. So you can see it looks like kind of a box here. We've got this rectangular thing with some numbers in it, and there's a line here. That is a matrix. That is a matrix representing a system of equations. And generally, not always, but like 95% of software that's going to solve systems of equations for you, you're supposed to enter that in the form of a matrix, because that's what, I talked before about linear algebra, which is basically it's a whole class and really a whole topic. There's many classes on it, just about this chapter. Some of you will take that when you finish the whole calculus series. Right? When you get done with your calculus, your next class will be linear algebra, which is a whole semester of doing this kind of stuff. So basically what we do is we take our system of equations and we turn it into this matrix form, and that's something that computer software can handle much easier than if we start putting things in with variables. So you want to understand, where does this matrix come from? Right? And I'll show you, we'll look in the book in a second, but I kind of just want to give you the idea. So a matrix is going to have these brackets on the end. Sometimes some books use rounded brackets, so it's more like parentheses on the end. But most common is that you see these square brackets that are on the edge here. Okay, so these square brackets. And what happens is what you might notice when you look at this matrix is you say, well, there's no system, or there's no variables there, right? I thought if we have a system of equations, we should have variables. And what happens is that's one of the convenient things about a matrix, is we don't have to write the variables, because the variables are inferred from position, right? Oh, and I just want to point out, I have a video in, I think I showed you. There's a video where I kind of go in depth with matrices here in Canvas, right? So you can watch that and you can see me talking about, and there's a matrix worksheet that you can go over. We probably won't have time to go over that in class, but there's a matrix worksheet you could follow along. But I sort of introduce a lot of that in that video. So if you're confused after today's lesson, go watch that video. In fact, go watch that video either way. Okay. So we have our bracket here. Now what happens is each column represents a position in the equation. So this is telling us we have two variables because we have two columns right here before this line. This line goes where your equal signs go, right? Remember when we had to put the equations the other day in that form, ax plus by equals c? So we were putting the variables on the left and the constant on the right. That's the way we basically always want to do that at this point, because this column represents our x variable. This column represents our y variable. This line here represents the equal sign. And then over here, these are what those equations are equal to. These are your constants. So your rows represent equations. So we have two equations here because we have two rows in our matrix. These columns over here represent different variables. If you had three columns over here, then you would generally call your variables x, y, and z. If you have four, W, X, Y, and Z. The letters that you choose for your variables don't actually matter too much. But there's sort of, you'll see, there's kind of a pattern to how we choose them. The line is your equal sign, and here's what they're equal to. And then this gives us a way that's actually more convenient. Now, I know a lot of times people get very confused when they first learn matrices and go, this seems like it's more trouble than it's worth. When you were giving me those two equations and two variables, I got to where I could solve them pretty quickly. And now you're giving me this big confusing matrix thing that I think is just too much work. Why do I have to go through that? And the answer is, for the simple case, you're right. You could probably solve a system of equations that is two variables in two equations faster by hand than you can with matrices. But as soon as you bump it up to the next size bigger, three equations and three variables, you're probably better off using matrices because it's a more streamlined process. It's one that's confusing at first, but once you understand what that process is, you're going to move through those problems faster, and you're going to get there quicker, right? So yes, many of the homework problems where it's two equations and two variables, you probably can do it by hand just as fast. But as soon as you get into more real world problems where you very rarely in real life do you just have two equations and two variables. Usually it's much bigger. And so at that point you say, I want to get this into a matrix, and then I want to get it into a computer so I can understand how this works or what my solution is. Okay, so let's see what that looks like. Let's go here to I don't know why that got so huge. It made the book enormous. I don't usually keep it that big. Let's make this bigger though. Still not big enough. That's a little too big. Oh. Okay, so they introduce in the book, they give you a matrix, and they say a matrix is just a table that consists of rows and columns of numbers called entries. This is an example of a matrix. Notice that this one doesn't have that line in it that we saw a minute ago. That's because there are numerous different types of matrices. But generally, for what some of you will learn that when you take linear algebra after calculus, after the calculus series. There are lots of different types of matrices, and you could do lots of different types of things with them. The specific thing we're doing in this class, we're really focusing on following systems of solving systems of equations. So we're using what's actually called an augmented matrix. An augmented matrix is that one we saw a second ago with the line through it. This one right here, this is called an augmented matrix because of that line. And that line is indicating to you this is where the equal signs go, meaning, oh, this represents a system of equations. That's what we're dealing with in this class. In general, yes, you can have matrices that do other things, and you might go, well, what else would you do with matrices? Matrices get used all the time. If you're a gamer, that game that you're playing is probably using matrices in some form inside of it in order to figure out what's happening to the graphics and how the graphics are changing and values changing and all sorts of stuff. It's almost guaranteed there is some type of matrices or equivalent operations happening inside that gaming. This happens if you use Photoshop or any kind of editing software to edit things. Your matrices are oftentimes being used in order to conduct those things. If you want to make your picture a little bit darker, or you want, anytime you make a change, it's probably being done with matrices inside of that software. So just be aware. Lots of things you can do with them. Okay, so then here we have a system of equations, right? And if you look, let's see, they kind of have them separated here. So basically what they do is they take it row by row. If you look at this system of equations here, notice we have 3 equations and we have 3 variables. We have some x's, some y's, and some z's. Notice that in this case, not every equation has an x, a y, and a z, but sometimes they will. Sometimes all 3 of your equations will have all 3 variables. Sometimes some of them will just have 2. It doesn't really matter, right? So notice what we do here is we basically take out the variables and just keep the coefficients. So see how if we take this first equation, negative x plus y minus 2z equals negative 7, if we just write the coefficients, we get negative 1, 1, negative 2, negative 7. And you might go, okay, but we got rid of those. But we can remember what those coefficients went with because of the position that they are in. The first position is the x, then the y, then the z, then the constant. Okay? And then we do the same thing with the second equation. So this becomes 3, because that's our coefficient on x. So that's where this, you can't see it on here. That's where this 3 is coming from. And then, we got a 0 here. Why? Because in this second equation, it's really plus 0y. And then plus 1z equals 5. So the second equation becomes 3, 0, 1, 5. Doing the same thing down here, we have 0x plus 3y plus 2z equals negative 2. Okay? So if we take all 3 of those and convert them where we keep the order in the right spot, but we change the, we just keep track of the coefficients, then you get this. So I can't really show both of them at the same time without making them too small, but hopefully you can see how this matrix right here came from this system of equations up here. It's the same number. Like you'll notice it's the same numbers, right? Like look here, we have negative 7, 5, negative 2. Look what we have here in the matrix. Negative 7, 5, negative 2. So it's the same numbers and basically in the same positions, and we're just making that matrix from it. Okay? So, and notice the line is going right where our equals were in the system. That becomes that line for our augmented matrix. And the coefficients over here become these coefficients right here. So it's one of those things where at first it looks really bizarre, but students actually are pretty good at going back and forth between having a system of equations, turning it into an augmented matrix, having an augmented matrix, and turning it back into a system of equations. Okay? That's kind of the first thing that you need to know, is how to go back and forth between the matrix and the system. Then what you need to know is how to do what they call elementary row operations on matrices. So when we have a matrix, the vertical pieces are called columns, and the horizontal ones are called rows. So you can keep that straight by thinking about, like, on a farm, you have rows of, say, corn. Those rows are running horizontally, right? And they say in front of a bank, if you have kind of an older bank or an older building or museum or something that has columns out in front, those columns move vertically, right? Columns don't go side to side. Columns go up and down in front of, like, the Lincoln Memorial or something like that. So rows are horizontal, columns are vertical, all right? So what we do is row operations. That's changing the rows So don't get that confused with column operations. So that's a whole different ball game, right? Column operations. So we're doing row operations. Hold on. Give me 1 second. All right, sorry about that. The printer had a job in the queue for some reason, and then it just started printing it. It like wasn't printing it earlier, and now it just started printing it, and it's like 4 feet from me, so it's super distracting. I'm trying to teach, and this printer's going. So sorry for the interruption there. So we have these rows, right? Remember, rows are the horizontal components of a matrix. Each one represents an equation. Okay, so remember back what we were doing with the elimination method is we were actually adding equations together sometimes, right? You would multiply an equation by something and add it to another equation. Well, if you think about it, that's kind of what we're doing here with our rows. If we add one row in our matrix to another, that's the equivalent of adding one matrix to another one, which we've already done as part of the elimination process, so it seems legitimate, right? So these 3 row operations will make sense to you if you think about the fact that rows represent equations. So our first row operation that we can use is where we can switch any 2 rows with each other. So we can take the first row and the second row and we can just switch them. You have to switch everything. You can't just move individual numbers around, but we can take the 2 rows and just switch the 2 rows. So I could take this row and switch it with this row down here. And if you think about it, well, why is that allowed? Because that's the same as just switching the order of those 2 equations that they represent. But if you rewrite the equations in your system of equations in a different order, that's not going to change it, right? Nothing's really going to change there. So that's allowable. Interchange 2 rows of the matrix. Our second operation is to multiply one row of the matrix by a non-zero constant. So we could take this first row, and I could just multiply everything by like 4 or 3/7 or -1/2 or whatever I want. You have to multiply the entire row by the same thing. But that makes sense too, because remember what we would do before when we were doing the elimination method? We would multiply the entire equation by some value. Well, that's what you're doing here. And when you multiply the entire row by some value, that's the same as multiplying the entire equation by some value. Okay? And then the third one is the one that actually confuses people the most, because they confuse it with the second one, because it starts off, you can see here when you look at it, it looks like you're saying the same thing, and then they take it to mean a slightly different meaning. So for row operation 3, we can multiply one row of the matrix by a non-zero constant and add the result to another row of the matrix. So what you want to understand about row operation 3 is only one row changes when you do that. Sometimes people try to make two changes because they treat this as two different steps. One is multiply one row of the matrix by a non-zero constant. They do that, and then they add it to the other step, but you don't. What you do is you sort of like, you multiply one row of the matrix by the non-zero constant, but you don't change values in your matrix with it yet. Like, you don't change that original row. You add it to another row, and those are the values that get changed. So just if you keep in mind, when you do row operation 3, only one row's values should be changed. If you're changing the values for 2 rows when you do row operation 3, then you're not doing it right. Okay, so that would mean like we could take the values from row number 1 here, we could double them and add it to this row down here. And the only one that would change is this row down here. We don't actually change the numbers in here to be doubled. We leave these values as is. We just take the doubled values and we add them in down here. That's what we're allowed to do. Okay? And those 3 row operations together basically allow us to do more than you could even imagine, right? The more than you could think, like the things that we can do with a matrix, and those 3 row operations, it really opens things up for us. They seem very simple, like, oh, there's like, that doesn't seem like we could do much. You can solve any systems of equations that way. That is solvable. You can do lots of stuff with it. So you have those 3 row operations. You'll get a little bit of practice with those in the homework. Make sure you're watching those videos, because I'm not really going to be able to go over these 3 sections today in like excruciating detail, and they have a lot of details to them. So make sure you're watching the accompanying videos and the videos that are in the homework to make sure you're really getting all the details for how to do these pieces. I'm trying to give you enough that you can kind of dive into it and see what's going on. So let's just see what a couple of these look like. So they want us to, here's a matrix, we're starting with it, it's augmented. So you should be able to look at this and be able to get back the original equation. So hopefully you can look at this and go, oh, that would be x minus 2y minus z equals 2 for the second row. If you can do that, then you're getting the hang of what we're talking about. So they want us to, 1, interchange rows 1 and 2. So see how down here we go from this matrix right here, to this one, because you take the first row and you just swap it with this row. I was thinking they were in a different row, but so in here, notice how they've got them labeled over here, rows 1 and 2. So you swap row 1 and row 2. Notice how the 1, -2, -1, 2 is at the top now, and the 0, 3, 1, -1 is in the middle. So row swap, easy to do. Step B, they want us to multiply the first row by -2. So we're going to take, so they're saying go back to the original. Let's see, do they want us to do it independently of one another? So what they're saying here, like, be careful when you do the homework with this. They're saying these are independent, not in succession. In other words, each time you do this A, B, or C, you're going back to the original matrix. You're not doing them one after another. In real life, you usually do a series of these row operations, and in reality, the computer does a series of row operations. But for now, we just want you to understand what's going on. So we're just kind of doing one step at a time. So for B, they want us to multiply row 1 by -2. So you're just taking that original row, which was, this was the original, 0, 3, 1, -1. And if we multiply everything by -2, we get 0, -6, -2, +2. Right? So you're just multiplying the row by -2. And then the one that's a little, where you kind of have to be careful, have some scratch paper so you can write values down. I see people trying to do the row operation 3 in their head. That's not a good idea. Don't do that. It's just, even people who are really good at math, it's just so easy to make a mistake in these matrices. And if you make one, it takes you so much time to go back and fix it. It's a huge pain. You're going to be much faster if you write this stuff down and then move forward with it. Plus, it also makes it easier to find your mistakes. So some people get frustrated because they're trying to do the stuff in their head. That is not a good idea. No one should be doing this in their head. Okay, step 3, multiply the first row by -2 and add it to the third row. Okay, so we take, what is it? Multiply the first row by -2 and add it to the third row. So here's our first row, here's our third row. So when we take -2 times the first row, we're getting 0, -6, -2, 2. And we're adding to the third row, which is 0, 6, -4, 5. So when we add those together, we get 0, 0, -6, 7. And that becomes our new row. So notice how for row operation 3, we only changed the third row. We didn't change the second. People have a tendency to do, they will write the -2s in here. They'll multiply by -2, and then they'll change the third row. Only one row should change when you do row operation 3. Okay? Okay, so now we get what's called row echelon form of an augmented matrix. Okay, row echelon form of an augmented matrix. So what this is this is a convenient form to get our matrices in. So at this point, you might be asking, like, wait, I don't really get what's going on with these matrices. What's the point? The point is, if you can put your matrix in certain forms, so it has like certain patterns of numbers in there, it becomes really easy to see what the solution to the system of equations is. Okay. And that's the one of those forms is called row echelon form. So in each non-zero row, so that just means a row that's not all zeros. It can have zeros, but the whole row can't be zeros when they say non-zero row. In each non-zero row, the first non-zero entry is 1. This 1 is called the leading 1. For any two successive non-zero rows, the leading 1 in the higher of the two rows must be further to the left than the leading 1 in the lower row. I know this is starting to get kind of confusing. I'll show you a picture in just a second that'll make sense of it. And each row in which every entry to the left of the vertical bar is 0, lies below all the non-zero rows. So what they're saying is basically this form right here. Where basically we call this the diagonal. So in the first row, first column position, second row, second column position, third row, third column position, those are called the diagonal. So these red ones here, those form the diagonal. Notice that everything below the diagonal is a 0. Okay, that's what they're talking about up here. So you get these leading 1s because that's the first non-zero value in that row. So the first time you go down a row and you hit something that's not a 0, it should be a 1. And then the numbers after it can be different values. But anything that's before that 1 should be a 0. Okay. This is saying, well, what if you have something that's zeros all the way across? Because that's something you get when you have a dependent system. Remember we talked about that last time? When you go about reducing a matrix, if it's a dependent system, you're going to get a row of zeros. If you get a row of all zeros, you should move it to the bottom of the matrix. That's what they're saying. So this is kind of the pattern that, like, you can, especially these first two, sort of think about those patterns. That's row echelon form. Okay. So what we want to do is take basically the goal here, and I don't have time to go through all the details. I'm going to have to switch here pretty quick. Take a matrix that's in, say, this form, that's representing a system of equations, and you want to turn it into something that's in row echelon form, in this form, using those row operations, those 3 row operations that we looked at a moment ago. Okay, that's the idea. So basically you can see here, they say solve this using Gaussian elimination. So you're given a system of equations right here. You're going to turn that into a matrix, which they do right over here. Right, so you can see going back and forth between the system of equations over here and the corresponding matrix, augmented matrix over here. And then you kind of look at it and go, what do I have to do to get it in row echelon form? And the thing is, there's more than one way to do it, right? There's more than one way to do these specific problems. But what you do is go, okay, well, I wanted a 1 in this position. And you go, okay, great, we already have it. Okay, so now you go down to the next row and say, well, the first non-zero value is supposed to be a 1. We don't have that. Well, what you could do is swap rows 2 and 3, and that would fix part of your problem. What they choose to do here in the book is to multiply row 1 by -2 and add it to row 2 to get a 0 here. So that's 2 different ways you could go about this problem. You'll end up with the same solution in the end, but don't get worried about like, well, I thought I should use these row operations. There's more than one way to do the problem, okay? And then notice how here they get a 1 in this diagonal position and a 0 in front of it. Now the goal is to get this 3 to be a 1 down here, and then they do that. So basically, in order to get the zeros where you want them, you're always going to use row operation 3. If you'll notice, like right here, we get this 2. We want that to be a 0. They use row operation 3 to get that to be a 0. So whenever you're like, oh, I'm supposed to get a 0 in this spot, use row operation 3. Okay. The reason that this is a convenient form is because it makes it very easy to find the... Wait, where did it go? I don't know why this thing snaps out of zoom mode sometimes. It's kind of annoying. Okay, when you're in this row echelon form like we are here, we have 1s on the diagonal and 0s below it. It's really easy to substitute back and get your original solution, because the way you would read this bottom one is just 0 equals 0.3, right? So that's why you see this equation over here. But then when we read this, we have y minus z equals 0. But we already know z because we got it right down here. So then you just plug z in here, and you can solve for y. And then look at our first row. X plus y plus z equals 1. Well, that's not too bad because we already know y. We just solved it down here. And we already know z. We just solved it down here. So you plug those in, and then you can solve for x. So it greatly simplifies having to solve these larger matrices, these larger systems of equations. Okay. And they give you the steps for how to do this, to do the Gaussian elimination. You want to do it in the right order. Otherwise, if you do things in the wrong order, what can happen is you end up undoing your own work. And that's obviously pretty frustrating. So what you do is you start at the first column. You get a 1 right here. And then you get zeros below it. Right? It's like sometimes it's tempting. You're like, well, what if I go over here and switch something? Then I can get a 0 over there. But by the time you get to that column, you may have undone that work anyways. So you start on the left and work to the right. So get your 1 in the right spot. Get the zeros below it. Then move to the second column. Get your 1 in the right spot. 0 below it. Then go to the next column, 1 in the right spot, right? And depending on how big your matrix is, you can keep going or you're done, right? Depending on what you're doing. So just make sure you're doing things in the right order. Otherwise, it's really frustrating. You make these row operations and you're like, oh, good, I got a 0 in the right spot. Now I got a 1 in the right spot. And now the next time you do a step, you go, oh, wait, my 0 went away. And you're like undoing that work. It's because you're not doing it in the right order, okay? They show you how to write it. I don't really have time to go over it, but they show you in the book how to write it when you have a dependent system, right? That's generally what you're going to get when you have more equations than variables. So this is something with, more variables than equations. We have 3 variables here, but only 2 equations. So that's a dependent system. It has infinitely many solutions. And the question is, how do we write those infinitely many solutions? It's great that there's an infinitely many solutions, but which ones are they? That doesn't mean everything is a solution. It just means, there's certain solutions and there's an infinite number of them, but it's not just anything can be a solution. So they show you in this problem how to write those. They show you in the videos in the book. And I believe I show you in that video that I have posted. Shows up as well. What about a system of equation with no solutions? Well, what happens when you reduce that? Let's zoom in on here. When you go through and you get it in the row echelon form, you'll see something like this. So notice what we have here, 0, 0, 0, -4. Well, how would you interpret that back into being a system of into the equation in the system of equations? Well, that would look like 0x plus 0y plus 0z equals negative 4. Well, how does that work? How can 0x plus 0y plus 0z equals negative 4? And the answer is it cannot. So the answer is no solution, right? So there's no, that's how you recognize a no solution type situation. And that's what's really great. You take your matrix, you put it into MATLAB or Maple or whatever you're using, whatever computer algebra system you're using to do this stuff. It gives you back some matrix, and you look at it, you see something like this, and you go, oh, okay, no solution. Right? Really, really helpful. Then we have a thing called Gauss-Jordan elimination. So the thing we just looked at a minute ago was Gauss elimination, and it was for row echelon form. Gauss-Jordan elimination is even better, and it's what we put things in for reduced row echelon form. So there's row echelon form and reduced row echelon form. Remember, row echelon form is where we had our ones and then zeros below it. Reduced row echelon form is where you have your ones and then zeros above and below it. Okay, so it takes more work to put things in reduced row echelon form, but the good news is once you do it, your equation is fully solved, right? Because how would you read this? You would read this as x equals negative 3, y equals 1/4, z equals 13/3. Your whole equation is solved for you. You don't have to do any other work. Remember with row echelon form we had to do that back substitution? Well, here you don't, right? You don't have to do that substitution. Because you just have the computer solve the whole thing for you all the way. If you're doing it by hand, you have to do a bunch of more steps, right? So you can see here in the book where they've got things in reduced row echelon form and then 2, -4, 1. Well, when you convert those back into equations, you have 1x plus 0y plus 0z equals 2. Well, that's just x equals 2. 0x plus 1y plus 0z equals -4. That's just y equals -4. So you can pull those equations out, that solution out very easily when you're doing it that way. Notice, oh, that's a little unusual, a little non-standard. Here they're using a u. So they use x, y, z, u. Again, it doesn't really matter what variables you use as long as you're consistent in them. Okay, so that's your introduction into matrices and how those work. Let's see if there's anything I want to point out on the homework. Yeah, watch the videos. You should be good to go. Okay, why don't I take roll before we go on? Okay, let's see. Janelle F. Mackenzie J. Chrisley K. Daisy R. If any of those people I just named are in here, get my attention. Okay. Okay, so with that said, let's move ahead to the next section. So we talked about that one. What do we have? Determinants and Cramer's rule, systems of nonlinear equations. Okay. For the sake of time, let me go over systems of nonlinear equations. I'll just give you a brief overview. I think the stuff in Canvas and Chrisley's here. Okay. Okay, gotcha. Okay, so right, let me just double check real quick here what we got. Nonlinear systems of equations. Yeah, right. So I've got a video here where I cover the nonlinear system, so watch that video. And then also there's a chemistry tutor video where they cover nonlinear equations as well. So between the two, you should have a pretty good understanding. But I just want to give you real quick an overview of what the nonlinear systems of equations looks like. So remember we talked about solving systems of equations like the following. Oops, let me put this in bold. So remember our discussion the other day about systems of equations, and we talked about how the intersection point of two lines was the solution to that system of linear equations. Okay, so the intersection point is the solution, right? Well, it's pretty easy with lines. There's only those three possibilities. Either the two lines cross each other and have an intersection point, or they're parallel and have no intersection point, or the lines are right on top of each other and they have infinite intersection points. Okay, let's see. Okay, Janelle, gotcha. So, so think about that, because like we know this red line doesn't like curve later and come down and cross the blue line again, right? How do we know that? Because they're straight lines. Well, that's one of the things you have to be careful about when you start talking about systems of nonlinear equations, because then you can get things like this. What's going on? Oh, I don't know. Desmos froze for a second. Okay. Okay, here we go. So now we have two parabolas facing the other direction, and look at what happens. We have two solutions, exactly two solutions. We couldn't get that before. Two lines can't intersect in exactly two places, right? It was either one place, zero place, or an infinite number of places. But now we have a situation where they can cross in numerous places. And we could even make this a little worse. X squared plus y squared equals, say, 9. And then let's make this a plus a. Add a slider here. So notice what we have here if we move a up high. So this would have no solutions because there's no intersection point. So this is a parabola and a circle, right? Okay, so let's move our parabola down right there. Oh, now there's one point of intersection. So there would be one solution to this system of equations. If I keep moving it, now there's two solutions to the system of equations. Okay. What about here? Oh, now it has 3 points of intersection. So now there's 3 solutions. If I go a little bit further, now there's 4 solutions. And, you can keep playing around. It goes back to 2 again and so on. So when it came to linear systems of equations, we were much more limited about the number of solutions we could end up with. In this situation where we have parabolas and circles and lines and, you know, all sorts of shapes, ellipses and all sorts of stuff, you can end up with lots of different numbers of solutions. As we just saw, if someone says, well, hey, there's a parabola and a circle, what are the, you know, how many solutions does it have? You go, I don't know, it depends. It could have 0, 1, 2, 3, 4, right? It could have any of those. So just be aware of that. When you're doing these problems, just because you find your first solution doesn't mean you're done with the problem. It means there might be 4 solutions and you have to find them all. So like we can see in the homework, I think it'll show, if I remember how they set these up correctly. Yeah, see here, they give you the spot for 2 solutions to put in there because they're saying this one has 2 solutions. Looks like they're keeping it pretty basic for this one. I forgot how many ones they went with. But you can have multiple solutions. It's not necessarily just one solution, and you get to stop looking. So make sure you watch the videos, because I don't have time to go on this one in depth right now. But make sure you watch the video, and then remember also inside of Canvas, there's a video here where I go over this exact topic, right, and talk about it. So you should be able to get the information by looking at that. Okay, with that said, let's spend the rest of our time looking at, what was it? Determinants and Kramer's rule. Okay, this is kind of confusing the first time you've seen it, so there's a couple chemistry tutor videos here, but I'm going to show you in the book. A little bit about determinants. So determinants are another one of those things where for a 2x2, it's real easy to do, but each time you make that determinant a little bit bigger, the work goes up exponentially, goes up a lot. So you might think, oh, well, isn't the determinant of a 4x4 matrix just twice as much as a 2x2? No, it's way, way, way more work. In fact, most of the problems that they give you that are going to be 3x3s and 4x4s, they do you a favor that you may not recognize right away. They put a lot of zeros in there because the zeros in these matrices make the work a lot easier. But if you take like this, a 2x2 determinant, we'll see in a second, really easy to find the determinant of this. Just like once you get the hang of it. But once you start getting down into like this 3x3, that's significantly more work than the one above, right? And if you give, I forget if they give us a 4x4, do they? I think maybe they don't. I think they stick to the 3x3s. But you'll see, the 2x2 is super easy. The 3x3, not terrible, but it's quite a bit more work. And if you do run across a 4x4, it's not fun at all. So make sure to watch those videos. They'll show you pretty easily how to do it. And I'll talk about it here while we go over the ebook. It keeps doing this where it makes this thing bigger and bigger. Let's see. Every time I open the textbook, it makes it larger than it was before. Okay, so determinants and Kramer's rule. And here's another, like I kind of mentioned earlier, I think we teach determinants too soon. I'm not sure why there's this big focus to teach determinants so far before people use them. Like you're not going to use determinants in Calc 1 or Calc 2. I think we use them slightly, like just barely use them in Calc 3 if I remember correctly. But it's not even like we do anything that hard with them. So you're learning determinants about a year and a half before you sort of need the things. So here we start off by defining the determinant of a 2x2 matrix. So let's just say we have a matrix. We're going to call it A because usually we give our matrices capital letter names, and the entries in the matrix get lower level letter names, lowercase names, just easier to keep straight. We have this thing called the determinant, which is a process that we run on the matrix It's a process that we run on the matrix, and it ends up giving us a number. Okay, so it takes a matrix feeds it into a function called the determinant, and the thing that comes out is a number. So you just I know I keep repeating it, but it's important because students get really confused here. You've got your function, the determinant. What you feed in is a matrix. What comes out is a number. Okay. Now, notice the notation is a little different here. I guess it's showing up on this. Yeah, you can see it well enough on this screen there. So notice how for the matrix, we use the square brackets. Well, this thing down here for the determinant, we use straight lines. There's a reason for that. In mathematics, a lot of times when something is what we call a metric, which is a measurement, basically you can roughly think of it as a measurement. We use straight lines. Like the absolute value is a measurement of a distance from 0. We use straight lines for that. The determinant also uses straight lines. So how do you tell the difference between a matrix and its determinant? Well, is it in the box parentheses or is it in just straight lines? That's how you're going to tell the difference. Okay? Now, how do we go about actually taking the determinant of a matrix? Well, this tells us that our formula is AD minus BC, which might seem at first like, wait, what? What's going on? What you do is you take the diagonal here, A times D, this diagonal, and you subtract from it this diagonal, B times C. Okay, so let's look at this one down here. What's the determinant of this -3, -2, 4, 6? You take this diagonal, -3 times 6. So you can see we've got that right here, -3 times 6. And then we subtract from it this diagonal, -2 times 4. So -2 times 4. So then you just simplify everything, and you get -18 minus -8 ends up equaling -10. Now, if you right now you're sitting there looking at that thinking, how could that possibly be useful in any way? I totally understand why you're thinking that. It turns out it's incredibly useful. The determinant of a matrix is almost always meaningful. Okay, it's almost always important. Sometimes it takes a little work to figure out exactly what the determinant is representing, but it's almost always important information. So for instance, like if you're doing a video game and some shape, you know, as the video game progresses, the size and shapes of things change, right? A lot, and I mentioned earlier, a lot of times what happens is a matrix is being used to change the shape of that thing on your screen, right? Well, the determinant of that matrix is off, depending on what you're doing, will often tell you about the change in area. What happened to this area? Did it shrink? Did it get bigger? What did it get bigger by a factor of? It can tell you information like that. And the negative sometimes means a flip occurred. So that shape may have been oriented one way, and as it moved across your screen, it also flipped. Now we're considering that a negative. So there's actually a huge amount of information encoded in the determinant. Unfortunately, you don't really learn all that until you really start using determinants. And for most of you, that's going to be a couple years from now, or some of you never, if you don't have to go that far. So you just kind of have to trust me that the determinant's really important. That's why I think they throw Kramer's rule into the mix and say, well, look what we can do with determinants. We can solve systems of equations with determinants. But for me, it's kind of a red herring, because you'll see at the very end of the section, they show you this Kramer's rule that we use determinants to solve systems of equations. They even say Kramer's rule can be used to solve systems of equations, but only in a very limited set of applications, such as computer graphics. For larger systems of equations, Kramer's rule quickly becomes inefficient, even with extremely fast and powerful supercomputers. So you can imagine, you know, your video games move pretty fast these days, some of them, depending on the type of game you're playing. Those shapes are changing so fast. You want to use, this is what computer scientists have to figure out, what's the most efficient way for me to calculate those determinants, calculate those matrices. And by their own admission here in the book, Kramer's rule is slow and inefficient, so you don't actually use those in the first place. So you generally aren't going to use Kramer's rule for much, right? But we teach it to you. So I just don't want to tell you that Kramer's rule is like a super important thing that you're going to use a ton of times in your life, but math teachers seem to really like it, just because then they can see if you know how to use the determinant. Which, as I already mentioned, probably should be taught 2 years later in the STEM sequence. But whatever, we have to teach it in this course. Okay, so that's how you find the determinant of a 2 by 2 matrix. Okay, so then how would I find the determinant of a 3 by 3 matrix? Well, then we get into this complicated structure that we can use to find the determinant of any size matrix. Now, the matrix has to be square. When we talk about square matrix, that means the number of rows is equal to the number of columns. So you wouldn't talk about the determinant of a matrix that has 2 rows and 5 columns, right? It has to be square. So that's why they say let A be an n by n matrix, right? That's rows and columns. So n rows, n columns. So they match. And let I sub j be each entry, right? Be the entry with the ith row and the jth column. So if they talk about entry I sub 3, 2, that means it's in the third row, second column. That's what they're telling you right here, okay? So we say there's this thing called the minor. The minor of Aij, denoted Mij, so M for minor, is the determinant of the matrix obtained by deleting the ith row and jth column of A. The cofactor of Aij, denoted Cij, is defined as -1 to the I plus j times the minor. Okay, so I know this is where it gets confusing, right? So basically what you're doing is, here's an example. So you start with this matrix right here, 0, 1, 3, -2, 5, 7, 4, 0, -1. They want us to find M1, 2. So that's the minor, where I is 1 and j is 2. So that's row 1, column 2. So what you do is you go over here and you, oops, sorry, I'm not showing it quite all the way. You cross out row 1 and you cross out column 2 and see what you're left with? This -2, 7, 4, -1. You just make a new determinant out of that. Basically, this is how it works, and it's why you can start to wrap your brain around why it gets so computationally heavy. If we want to solve we want to figure out the determinant for a 3 by 3 matrix, we break it down into 3 2 by 2 matrices and then figure out the determinants of those. So whereas to figure out the determinant of a 2 by 2 matrix, you just do you do the determinant calculation one time. For a 3 by 3 matrix, you have to do it 3 times. Okay, and it gets even worse. For a 4 by 4 matrix, you break it down into 4 3 by 3 determinants, and then those 3 by 3 determinants have to get broken down into 3 2 by 2 determinants. So you can start to see that exponential difficulty that arises that we get from breaking down these determinants into many, many smaller and smaller determinants. It's a lot of steps taking place. So let's see, what do we got? A few more minutes. So just be able to go through, calculate the minors, and then for the cofactor, you take -1, and then you add the row plus the column number, the index for the row plus the index for the column. So this would be -1 to the 3, which is -1, times the determinant of your minor, and you end up with this calculation. Okay. So, right. So then to find the determinant of an n by n matrix, you basically do that by choosing any row or column that you want, and you do what's called cofactor expansion. So you can go down one row, you can go across one column. And you might go, well, what's the difference which column or row I choose? Won't I always get the same thing? And the answer is yes. But generally what you want to do is you want to choose the row or column that has the most zeros in it. So like right here, we have a 0 here. So first row, first column both have a 0. What is this? Second column, third row, those have a 0 in it. So it would save you steps to choose the one with the most zeros, because you can see what happens when you're doing the cofactor expansion. If your lead term is a 0, then it cuts this whole thing to a 0, and you don't actually have to do that computation because you're going to end up multiplying it by 0 in the end. So it saves you one of your 3 computations that you have to do with this step. So that's nice. If you have to do 3 things, then all of a sudden you only have to do 2. That's convenient. So when they say choose any row or column, the key is find the one with the most zeros in it and expand across that. Step 2, multiply each entry in the chosen row or column by its cofactor. The determinant is the sum of all the products found in step 2. So basically, if we were to go like what they're doing, they're going across the first row. So you take the cofactor of the first one, plus the cofactor of the second, plus the cofactor of the third, and they calculate all three of those, knowing the first one is 0, so it saves us some calculations here. You actually calculate these two, and you end up with negative 34. So that's how you do the that cofactor expansion. And all Cramer's rule is a way of taking determinants to solve your system of equations. Okay, so there'll be videos in the on those homework problems where they show you how to do that one. Right, let's see. Like here on the homework, see how they say find the value of the following 3 by 3 determinant? Well, you probably want to go across that first row because there's 2 zeros there. That's going to be way fewer steps than if you decide to go across the second row. Okay, so look for that when you're doing these. Yeah, so here when they say use Cramer's rule, notice there's the video. Just follow along with the video. Okay, just sort of watch what they do in the video because I have 2.5 minutes. I can't really go over Cramer's rule. So make sure you watch those and you see how to do those. And then let's just see, is there anything I need to announce? I don't think so. Make sure you're watching the homework due dates. Let's go back and just look at the calendar real quick. So you've got your chapter 5 stuff is due Sunday. So that gives you a few more days to work on that. And then really you want to start chapter 6 if you can get into it. Chapter 6, there's not a lot of, I'm not saying it's easy, but there's not a lot of concepts going on. It's pretty much just plugging stuff into formulas. So that's something that you probably could do even before Tuesday if you wanted to get started on that. You probably could get through a fair amount of that chapter just by looking at the formulas in the book and following along. It's not like matrices where, you know, there's a whole lot of details going on. It's pretty much, here's a formula, do what's in the formula. That's how chapter 6 works, I'm saying. Okay, so with that, I think we're good. Make sure you have your appointments set for the test. You do not need a Scantron. You'll be writing out your answers in a traditional form. I will be giving partial credit, so make sure that you show your work. The practice exam is posted. You are encouraged to get help from tutors looking at that practice exam. You are encouraged to work together in study groups to get yourself ready for that test. Whatever you need to do, make sure you bring your graphing calculator and obviously your photo ID, because otherwise they won't let you use the testing center. Okay, so I'm going to close down the YouTube stream. Anyone who wants to talk to me, please hop into the Zoom meeting, and I can talk to you. Otherwise, I will see you next week. Again, finish strong, right? This is kind of a big weekend for, you know, make sure you're caught up on the homework, make sure you're getting yourself ready for the test, and then you'll be ready to finish strong next week. Okay, thanks everybody. Have a good